Okay, we'll start today's lecture. This is our third lecture in lasers. Today we are understanding what are the conditions necessary for laser action. The last class you have seen that the requirement is the metastable state and the population inversion. Today we'll understand in brief, in detail, the exact conditions for laser action, and then we'll go for the requirements for any laser system. What are the requirements to get a laser? So for any laser to get, there is a need of stimulated emission. That's what the LASCR stands for, light amplification by stimulated emission of radiation. So stimulated emissions are the necessity. If there are no stimulated emissions, you will never get the laser. Therefore, to get the stimulated emissions, see, stimulated emission will certainly does from an excited state. So you know that if you have taken a system or a material, there will be n number of atoms. Each atom having its own energy levels E1, E2, E3, and so on. So there will be plenty of energy levels from E1 to En. So all these that is the lowermost energy state is always called the ground state energy, and any other level above this ground state, that is E1, are called the excited states. These excited states have a lifetime of around 10 to the power minus 8 seconds. You know that under normal condition at any temperature, the probability of the lifetime of the excited states is around 10 to the power minus 8 seconds, that is around few nanoseconds. Okay, so now there are many such excited states, and you know that in the last class also learned that the number of atoms as you go up from the ground state, that is you are going from the energy level E1, E2, E3, E4, etc., and so on. The number of atoms they present at the level E1 is called the N1, and the number of atoms that are present at the level E2 is called as N2, and in E3 it is N3, and so on. As you go up from E1 to En, energy is increasing. E1 energy is increasing. E1 less than E2, less than E3, less than E3, and so on. But the number of atoms you look at, N1 is greater than N2, N2 is greater than N3, N3 is greater than N4, like that. As you go up, the number of atoms of the particles decreases. The lower one is more, upper one is lesser, like that. Okay, energy levels increases, it is E1, E2, E3, like that, but the number of atoms in those energy levels distributed, as you go upwards, it is decreasing. It means the lower levels always occupies the higher number of atoms. So now I told you that in a system there will be a billion of atoms. You cannot count by 1, 2, 3, 4 as a number. Therefore, there is some probabilities associated with their distribution of atoms in the various energy levels is given by the Boltzmann factor. Here Nj is the upper level, Ni is the lower level. So between these two levels, Nj is the number of atoms in the upper level, Ni is the number of atoms lower level, ith level. So between any two such levels, number of atoms is given by the ratio Nj by Ni, that is equal to e to the power minus Ej minus Ei by Kt. So that is the distribution of atoms in the various energy levels is given by the Boltzmann factor. Under normal conditions, you know that the upper level is less than the lower levels. So we need to achieve population inversion. What is this? What do you mean by population inversion? Look at the diagram here at the bottom. The left one is the normal condition, normal population. Look at that E1 contains more number of atoms, E2 contains less compared to E1, and E3 is contain less compared to E2. Like that, there is a distribution of atoms. This is the normal condition for the distribution of atoms in a system. But we need to achieve the population. Look at the right side, the E3 got N3 number of atoms, E2 got the N2 number of atoms. Look at N3 is greater than N2. You need N3 is greater than N2. You need to achieve this particular state to get the population inversion. I mean, this is population inversion. Once you got this population inversion, other things will follow. So the laser can be stimulated emissions can be initiated, and lasers can be produced. Therefore, the population inversion, how to define the population inversion? The population inversion is the condition of the material in which the population of upper energy levels Nj, that is upper level, exceeds the population of the lower level. This is the meaning of, I mean, definition of population inversion. In population inversion, Nj must greater than Ni, where J is greater than I. Okay. Here N3, with respect to this diagram here, N3 is greater than N2. So in this condition, in the previous diagram, you've seen that there is the population between the energy levels Cj and Ei are inverted. When the under the ordinary case, Ei should be more, Ej, I mean the atoms at Ei should be more, Ej should be, that is Nj should be less, but it is inverted. So that is called the inversion. That is population inversion. This is the non-equilibrium state. Okay, this is not the equilibrium condition. Under the equilibrium condition, you have seen that the first diagram in the first of the in the previous diagram, the previous slide, the first diagram is the that is a normal state. That's equilibrium state. The non-equilibrium state is the second one. So, a population inversion is a state of non-equilibrium. The population can be how to achieve this N3 greater than N2. This can be achieved by a mechanism called the pumping techniques. By outside, you can make you artificially can be introduced, you can artificially can be generated this particular situation called the population inversion by certain techniques called the pumping techniques. What then, how to define once again the pumping? It is a method of exciting the atoms from the lower level to higher energy level by the supply of energy. That is, you are pushing the atoms from lower level to the higher level by using energy. By supplying energy, you are making the atoms from lower state to higher state. You are pushing the atoms from lower to higher state. So, by the supply of energy, in order to achieve population inversion is called the pumping technique. There are many techniques under pumping. One of them is called optical pumping. In this optical pumping, external light source, the external light energy is used to excite the atoms to higher energy levels. So you are using light energy to push the atoms from lower to higher levels. That is optical pumping. In electrical pumping, it is the electrical discharge that makes the particles in the lower level to move to higher levels. So again the situation is same. You are moving atoms from lower to higher level by making use of electrical energy. Similarly, by using heat energy, you can excite the atoms to higher energy levels. These are the different kinds of achieving population inversion. So this is to get a laser, you must achieve first the population inversion. So you must achieve population inversion. Once it is now the population inversion cannot be achieved in every energy excited level. It is not possible in every excited level of chosen. Okay, there is some restriction for this excited state. That is, these atoms are going to the higher states, so this they are remaining there and then comes back to the lower state. That's how it creates the lasers, the emission of photon. That's the laser. To achieve the laser from the excited state, I told you this particular excited state is a special kind of an excited state. What do you mean by that? See the lower state, look at the diagram. Lower state, the ground state, it is a ground state. The very first state is the ground state. Any states above E1, they are called the excited states. That's E2 is the excited state, E3 is another excited state, E4, E5, like that. All are excited states only. Within that all those excited states, there is one particular state that is also a excited state. We call it as a metastable state. What is the speciality of this metastable state? The lifetime of this metastable state is much higher than the ordinary excited states. In ordinary excited states, where the atom can sit up to 10 to the power minus 7 to minus 8 second, and up to, or it is about a few nanoseconds. So the atom in the excited ordinary excited state has got the lifetime of 10 to the power minus 7 to minus 8 seconds. But the special state, what we call the metastable state, which has got much higher lifetimes. That is, this particular special state, special excited state, has got the lifetime of around 10 to the power minus 3 seconds. It is some around milliseconds. So now the atom can sit in this metastable up to millisecond. Such a state should be identified in a system so that from where you can achieve the laser. If suppose you don't have a system where the metastable state does not exist at all, then it's never, there will be you cannot achieve population inversion and as well as the laser. It means if the system does not have a metastable state, you will never achieve the population inversion and you will never achieve the laser. So, metastable state is a must to get the laser output. Okay. So, the first, see, if you have a metastable state, then you can achieve population inversion. Otherwise, you cannot achieve population inversion. Look at the diagram. The ground state, the atoms have been pushed to the state, the upper one, it is E3, we called it E3, and E3 state is it's not permanent state. It has to descend, it has to come down to lower state within 10 minus 7 to minus 8 seconds. So it is coming down. On its way down, let us say that is going to sit at the metastable state whose lifetime is around 10 to the power minus 3 seconds. So it is going to rest in this metastable state for a long time. So within this long time, there is continuously the atoms have been pushed from the ground to the upper state and then they are collecting, accumulating at the metastable state. It's kept on going. So there you will see that there is a collection of particles have been at the metastable state. So within this milliseconds, there will be large number of particles accumulates at the E3. Now, from E3 to ground state, there is large number of particles that accumulates at the metastable state E2. So now, since when such large number of atoms accumulated at that state, a spontaneously passing photon from outside, let us say, there is within the system a spontaneously created photon whose energy difference is E2 minus of E1 photon that now will come and hit this bunch of particles sitting at E2. Once that is initiated, there will be a large number of stimulated emission that arises and that you learnt in the last class. So a spontaneously created photon whose energy difference is that of E2 minus E1 will triggers the stimulated emissions. Once it is triggered, you will have a plenty of photons, a bundle, n number, a billion, a large number of photons starts and coming downwards to E1. So that is the red waves, they are the laser now. So that's how a laser beam is created. So here you have seen that it's already understood that when you look at this slide here, we have considered a system contain n number of atoms with energy level C1 less than E2 less than E3, and the atoms have been in those particular levels N1, N2, N3, that is N2 N1 greater than N2, N3, E3. An atom excited to E3 may stay normally around 10 to the power minus 8 second before spontaneous emission. Even though the atoms continuously pump to E3, they undergo spontaneous emission and return to lower state. Population inversion cannot be achieved at E3, it is achieved at E2. Okay. So we have seen that when a bundle of photons will be created, that is called the laser, that is you require a metastable state. We already seen in the previous diagram, you require a metastable state. So in order to the atoms So once the metastable is achieved, we have seen that N2 is much greater than N1, that is the population inversion. So then once the population is achieved, a spontaneously created photon will trigger the bunch of transitions from E2 to E1, giving out the laser output. If there is no metastable state, no population inversion achieved and no laser is going to get. Okay. So to get laser, the requirement, the condition to get a laser is the requirement of the population inversion, that is the achievement of population inversion. This population inversion is achieved only in the state called the metastable state. This metastable state has got the lifetime of 10 to the power minus 3. Therefore, the atoms particles coming from the higher states will start accumulating at this metastable state. So once they such as when you look at the number of atoms sitting at metastable state with a lower state, you see that N2 is very much greater than N1. Once the situation of N2 much greater than N2 is N1 is created, a spontaneously created photon will trigger the bunch of photons. That's the laser. So now what are the requirements? So what you require to get the laser output? So you require some raw materials, some ingredients, no, to get an output like that. Our need is to get the laser. To get laser, what are the components are essential? Okay. So these components are classified, defined as an exciting source, an active medium, and the or optical resonator, or it is called the laser cavity. So these are the three components of a laser system. A laser system contains three major components. They are an active medium, an excitation source or a pumping agent, or and an optical resonator. It is called also a laser cavity. Look at the diagram. The central one, active medium, red arrows, that is the active medium, and you got two blue lines on the either side, a total reflector return, and on the right side is a partial reflector. These are the two mirrors. The blue ones are the mirrors, and the gap between the two mirrors is called the laser cavity. The gap between the two mirrors is called the laser cavity. So now the photons, they have been created in a system, in a medium. So that is called the active medium here. So you require a medium where the photons have been created. That is the active medium here. That is called the active medium. See, in an active medium, there may be some other material also. So it may be some other impure, some other maybe also. So now, all see the meaning of active is that only those molecules there where you will get the laser output. There may be some other materials, they simply remain there as passive components, passive material. So the active material, the active centers where you get the actual laser, the wavelength, the laser. Okay. So I will discuss in the next slide. So you require a medium where the photons have been created, where there is stimulated emission created, where you have a metastable state, where you produce a population inversion, and so on. That is the active medium. So now you are seeing ultimately the photons are coming out of the partially reflector side. Okay. So you got the photons out. They possess certain energy. Where does this energy come from? This energy is come from by an external exciting source. So you have an external exciting source, that is pumping agent. You already seen that in the previous slides. The pumping agents, that is how the atoms have been pumped, that is thermal pumping, electrical pumping, optical pumping, etc. Know that. So optical energy gives that is optical energy, the energy taken from an optical source where you have the optical exciting source. If the energy is taken out from an electrical source, it is an electrical source, exciting source, like that. Okay. So you require some source that gives energy to the medium active centers in the active medium. So from where it is again released back. So once the photons are released, they are moving between the two mirrors, that is blue ones. So it is moving between the two mirrors and it builds up. Since the total reflector on the left side, that mirror is 100% reflection, has a property, reflecting property, does not have the transmitting property. Therefore, photons won't travel out of the total reflector side. So it comes through a partially output partial reflector side. Okay, we will see that. And something now coming to active medium. So it contains three major components. The first one is called the active medium. What is an active medium? It is a medium in which where excitation can be, I mean, it is a medium when excited, it reaches a state called the population inversion and provides stimulated emissions. Finally, that leads to the amplification. A medium where you can achieve stimulated emission. How it is achieved? The particles got excited to the metastable state, so it creates a population inversion. Once the population inversion is achieved, you can see the amplification of light. So, I told you within the active medium, all atoms are need not be active, some are them are passive also. So they behaves as host to these active materials. So only a small percentage of atoms of particular type have energy levels as suitable to achieve population inversion. There are some other passive, they don't take part in the population inversion. Only certain active materials, centers, active centers, where population inversion can be created. Once you create the population inversion, you can stimulate the stimulated emission. So the medium hosting all other than active centers is called the host, and finally it is together is called the active medium. The medium, okay. So in a medium there may be other atoms also. They may not be actively participating in getting the in achieving the population inversion. Only there are only small percentage of particular type of atoms are there where you can achieve population inversion. That leads to finally creates the stimulated emissions and the amplification of light. Okay, the second component is the excitation source. Without excitation source, the photons, you cannot achieve the population inversion. You cannot push the atoms to higher energy levels. So the external agent that provides the energy, I told you it can be optical pump, it can be optical pumping or a thermal, electrical pumping, etc. and so on. So energy is supplied from outside. For achieving and to maintain the condition for population inversion, we need to raise the atoms continuously to the upper level. This requires energy that is given out from an external mechanism. Okay, that is called the pumping. Pumping is a process of supplying energy to the atoms to achieve population inversion in the metastable state. So there may be different pumping techniques, you know that. So from this external source, the energy supplied to the particles within the active medium. So they picks up energy and goes to the excited state. So this particular excited state is such a way that it is called the metastable state. This is called metastable state because whose lifetime is much higher than other excited states, whose lifetime is around 10 to the minus 3 seconds. Therefore, the particles accumulates up to 10 to the minus 3 seconds. There will be large number of particles have been created, and this particular energy level there creates a situation called population inversion. In population inversion, you see that N2 is very much greater than N1. Once such a situation is arrived, a spontaneously created photon will trigger the bunch of photons that is ultimately called the laser. Look at the, I mean, then see, There is a third component is called the laser cavity. What is that laser cavity? You have seen in the diagram the blue lines that they are the places, they are the mirrors actually. To the left 100% reflector, on the right side you got another. So between these two the cavity is called the laser cavity. Two mirrors along with the active medium forms the laser cavity. A laser device contains an active medium bonded by the two mirrors such that one of them is completely silvered and the other one is partially silvered. The photons, once they are released within the active medium, they move along the to and fro motions. They move because you got two mirrors. The photons that is released kept on moving horizontally, and he sees the mirror and one side, so it gets reflected, kept on moving. While on its move, you know that it creates more stimulated emissions. You have seen in the last class. So once a passing photon that creates two photons that will induce two transitions. So from these two transitions, four photons are released. From when four these stimulated emissions will create four more transition, release the four more transition, release eight and so on. So that they have been kept on moving along the horizontal length of the active medium. So and that's how it builds up. So the what is laser cavity? It is the distance between the two mirrors. So here, look at, the photons are moving. You suppose this the laser cavity L should be arranged such a way that it is equal to n times lambda by 2. I'll tell you what is it in the next slide. The distance between two mirrors should be arranged such a way that you will create or you will amplify the laser signal. I'll show you in the next slide. Look at the diagram. See here, the atoms have been created initially in the beginning. The atoms have created. They are moving along the length of the horizontal length of the active medium. The leftmost is one mirror, is completely silvered. On the right side, you got partially silvered. Some photons have been created in other than the horizontal direction also. So these photons will won't be uh, they don't contribute to the final laser. So they will be lost. So now as it moves along the horizontal line, so it is created they are nothing but the stimulated emissions. The two stimulated photons will make 4, that 4 will make 8, 8 will make 16 and so on, so that the bundle kept on, the number of photons kept on increasing. Look at the third, the lowermost diagram. So you got a large bundle of photons now. It is almost overcrowded. Once the situation that has been achieved within short time, and now the laser will come out of the right side, the partially silver mirror. So that is a laser output. So that's how it is going to happen. So the distance between two mirrors is called the laser cavity. Here I said the light is coming out. This light possesses a certain wavelength lambda. So you need to adjust these two mirrors by a condition called, it is integral multiples of lambda by 2. L is the length between the two mirrors. L is equal to n times r. That's integral multiples of lambda by 2. If you maintain that, then you will get this particular laser. If the distance between two mirrors doesn't satisfy the condition, that's equal to n times lambda by 2, you will not be able to achieve laser action. Okay, so that is the thing here. You will see that in the next slide. See here, I'll read out. Because of the reflection from the mirrors, one set of waves moving. You have seen that moving from right to left and other from left to right. Two waves interfere constructively because two waves are moving. You know that you understand the interference of light. Two waves interfere constructively if there is no phase difference, and it does destructive if the phase difference is 180-degree. Okay, so to achieve, see in our laser, we are getting laser output means it is undergone the constructive interference. If the distance between two mirrors does not satisfy the condition, that's L equal to m times lambda by 2, it will undergo destructive interference. To achieve constructive interference, you must maintain the distance between two mirrors such a way that it is m, that's integral multiples of lambda by 2, where lambda is the wavelength of that particular laser. So you need to maintain this particular distance, otherwise it results in the destructive in nature and you don't get the laser output. That is very important. So in such a case, the waves that is being created in the cavity is got the L is equal to, I mean, it should be from this you can get the wavelength lambda is equal to 2L by M. Here written again it's L is equal to M lambda by 2. Actually, I should write here lambda is equal to 2L by M. That is the wavelength of the light is produced. Okay. You know from this interference, when two waves, look at the wave 1 blue and red to wave 2, when they match, the amplitude matches, you will get the amplitude increase in amplitude. If the waves are having a phase difference of 180-degree, it will not produce the output. It is in destructive in nature. Okay, to get the laser output, the phase difference should be 0. If it is 180-degree, it creates the destructive also. And also the you see that the distance between two mirrors should be around n times the integral multiples of lambda by 2, otherwise you will not achieve the constructive interference. Okay, so this is the completion of this but today's class. So I completed today's class. So now is there any